Okay, here it is, the fundamental theorem of calculus, the big kahuna. Okay, now credit for this goes to Isaac Newton and Gottfried Leibniz, and what they found a connection to the tangent line problem for differentiation and the area problem for integration. The theorem basically uses the inverse relationship between differentiation and integration. Okay, so basically, if you go back and we know the slope of the tangent line was found by using the quotient, the change in y with respect to x. The area problem actually used a product of delta y times delta x, width times height, thus the inverse relationship. The fundamental theorem of calculus states that the limit processes used to define derivatives and integrals will preserve this relationship. So I don't want to confuse you too far, but basically this fundamental theorem of calculus comes from that inverse relationship. So let me just give you the fundamental theorem of calculus. If f is a function that is continuous on some closed interval from a to b, in other words, there's no breaks in it, and capital F is an antiderivative of little f on that closed interval, then we can say that when you integrate this function where you're integrating from x equals, so if you want to think of those as x equal a to x equal b, but we don't write the x, but we're integrating from x equal a to x equal b of the little f of x dx, then basically it turns out that the way you evaluate this integral is you take the antiderivative and evaluate it at b minus the antiderivative evaluated at a. Now, this a is called the lower limit of the integral and b is called the upper limit of the integral. So basically you're going to take an antiderivative evaluated at the upper limit, then minus the antiderivative evaluated at the lower limit. And so that's how you evaluate a definite integral using the fundamental theorem of calculus. Okay, so now if we wanted an example, we could actually find area by using this fundamental theorem of calculus. So let me just show you. If we wanted to find the area of the region bounded by the graph y equal x cubed, the x-axis, and the line x equals 0 to x equal 2, well, basically it would look like this. So this is a rough example of what y equal x cubed looks like. And then, of course, it crosses the x-axis at 0, so here's x equals 0, and then here's x equal 2. And notice I'm showing you that it goes up, the line x equal 2 goes up and touches the graph here. Now, basically, what we would be finding is it would give us the area bounded by the x-axis, above the x-axis, below the function from 0 to 2. So basically we would be finding the area in here by evaluating this integral. So let me show you how to do that. All you have to do is we integrate from 0 to 2 x cubed dx. Well, the antiderivative of f of x is x to the 4 over 4. Now normally I say plus a constant, but here's the good news. With the fundamental theorem of calculus, you don't have to put the constant because when you subtract, the constants cancel out anyway. So all I have to do, I can just use the antiderivative that doesn't have the c with it. So now evaluate that antiderivative at the upper limit 2. So evaluate that antiderivative at 2, and I get 2 to the 4th over 4, which is 4. Then evaluate it at the lower limit, which is 0, and then I get 0 to the 4th over 4, which is 0. And then so the answer to this is that I simply take the antiderivative evaluated at 2 minus the antiderivative evaluated at 0. So the answer is 4 minus 0, which is 4. Now, there's a notation that we can use to show this, and here's the notation. If we want to evaluate this definite integral from 0 to 2, basically we find the antiderivative x to the 4th over 4, And then this notation just shows you that I'm going to evaluate it from the lower limit 0 to the upper limit 2. And then over here I do the evaluation. So I evaluate this function at 2, then I evaluate this function at 0, and I take the difference between the two, and I get 4. So that's how you apply the fundamental theorem of calculus to evaluate a definite integral. Okay, we'll get away from the area application for now and just focus on how do we calculate or how do we evaluate definite integrals. Okay, so here's a definite integral evaluated from 1 to 3 using the function 2x. Well, you know how to evaluate, or you know how to get an antiderivative of 2x. You can just use the power rule, so you get 2 times x squared over 2, and then the 2's cancel, and you just get x squared. Remember, we don't need the constant with definite integrals. So we're going to evaluate this function from 1 to 3. So we evaluate this function at 3 first, get 3 squared, and then subtract what we get when we evaluate at 1, which is 1 squared. So 3 squared minus 1 squared is 8, and that's that. We can do one a little more complicated. If we integrate the square root of x from 1 to 4, well, we would have to write that as x to the 1/2, and then to get the antiderivative of that, use the power rule. So that would be x to the 3/2 over 3/2. Okay, and that would be, hang on just a second. Okay, let's start over here on this one. What I meant to do here was integrate square root of x over 2. So let's do it again. Ignore that little mark there. So square root of x over 2, I can factor the 1/2 out, and then I can write square root of x as x to the 1/2. So I'm integrating this from 1 to 4. So if I integrate x to the 1/2, I'm going to get x to the 3/2 divided by 3/2. But then remember, I've got this 1/2. So 1/2 times that. Well, 1/2 times 2/3 just gives me 1/3. So I actually get x to the 3/2 over 3 evaluated from 1 to 4. So now I have to evaluate this function at 4, which would be 4 to the 3/2 over 3, and then minus the function evaluated at 1, which would be 1 to the 3/2 over 3. So that would be, the square root of 4 would be 2, and 2 cubed is 8, so that's just going to be 8 over 3. And then 1 to the 3/2 is 1, so I'm going to have 8 over 3 minus 1 over 3, which is just going to be 7/3. So again, the original function should have been square root of x all divided by 2 for this problem. Okay, now this next one I'm integrating from 1 to 2, and so you know how to get an antiderivative of this. So you just use the power rule and your other rules for integration. And anyway, you should get 2x cubed minus 5x. And I'm going to integrate that from 1 to 2. So basically what I'm going to do is I'm going to take this function and evaluate it at 2. So I get 2 times 2 cubed minus 5 times 2. And then I'm going to subtract that same function evaluated at 1. So I'm going to put 1 in everywhere there's an x. And you can check my arithmetic, but I got 16 minus 10 for the first expression, which is 6, and then 2 minus 5 for the second expression, which is -3. So 6 minus -3 is 6 plus 3, which is actually 9. Okay, let's take a look at this one. If I want to integrate e to the 2x dx from -1 to 1, well, remember, there's a little trick for this. E to the ax dx can be integrated as 1 over a e to the ax. So I can write that as 1/2 e to the 2x. And if I evaluate it from -1 to 1, I can evaluate it 1/2. If I plug 1 in here, that's going to be 1/2 e squared. And then minus, and then if I plug -1 in here, I'm going to get 1/2 e to the -2. And if you factor the 1/2 out, you'll get 1/2 times e squared minus 1 over e squared. Okay. Now you can actually factor the half out before you apply the fundamental theorem of calculus, and sometimes I do that. Okay, here's one we did, well, I don't think we did one exactly like it, but we had a similar problem to this in definite integrals. This one I'm actually going to factor the top e to the 2x minus 1 is difference of squares, so it factors into e to the x minus 1 times e to the x plus 1, and then I can cancel this. And that'll cancel as long as x isn't 0. And since we're integrating from 1 to 2, we know x is not going to be 0. So I end up with just this, the integral from 1 to 2, e to the x plus 1 dx. Well, when you integrate e to the x, you get e to the x, and when you integrate 1, you get x. And now evaluate this at 2, and I get e squared plus 2, and then minus evaluate this at 1, and I get e to the first plus 1, and then remove the parentheses, and I get e squared minus e plus 1, because 2 minus 1 is 1. And this is the exact answer, and 5.671 is an approximation. Here's another one, 1 over x minus 3 dx from 1 to 2. Well, you know how to integrate 1 over x. It's just natural log of the absolute value of x, and you integrate minus 3, you get minus 3x. And then you evaluate that from 1 to 2. So first evaluate this at 2. So I get natural log of 2 minus 6. See, 2, absolute value of 2 is 2, so I can get rid of the absolute value. So natural log of 2 minus 6, and then minus evaluated at 1, natural log of 1 minus 3. And so I get natural log of 2 minus 6, and natural log of 1 is 0, so that's minus 0 minus 3. So that's actually natural log of 2 minus 6 plus 3. So minus 6 plus 3 is minus 3, so you get natural log of 2 minus 3. And natural log of 2 minus 3 is the exact answer. Negative 2.307 is the approximation. One more. If I integrate this from 0 to 1, I get, if you integrate 3e to the x minus 2, you actually get 3e to the x minus 2x. And if you evaluate it from 0 to 1, if you evaluate this at 1, you get 3e minus 2. And if you evaluate it at 0, you get 3 times 1 minus 0. So you actually get 3. So you get here, you get 3e minus 2 and then minus 3, which is 3e minus 5 for the exact value and 3.155 for the approximation. Now here I've given you 3 problems with the answers. I checked these on the computer, so they should be, the answers should be correct. So you can practice on those problems and see if you can get those answers. And if you can't, you know, let me know if you suspect an error. Okay, I'm going to show you a little tricky one here when you have an absolute value. So here it says evaluate from 1 to 3 the absolute value of 2x minus 5 dx. Well, what you have to understand is that the absolute value of 2x minus 5, if 2x minus 5 is greater than 0, and for it to be greater than 0, you could solve this and say x is greater than 5 halves. Okay, so when 2x minus 5 is greater than 0, you're just going to get 2x minus 5 halves. So that's going to be true when x is greater than or equal to 5 halves. But 2x minus 3 is going to be negative if x is less than 5 halves, so you would actually be integrating the minus 1. So basically what you have to do here is break this up into 2 integrals. So you have to, when x goes from 1 to 5 halves, which is 2.5, you're actually integrating the minus 1, which is 5 minus 2x. So I'll let you see how I integrate that, but you integrate that and then you get 9/4. But when you integrate from 5 halves to 3, you're actually integrating the plus 1 because that's where 2x minus 5 is positive. So you're integrating the plus 1. And then, so when you integrate that, you get x squared minus 5x to 5 halves from 5 halves to 3. And I'll let you evaluate this. And I got 1/4. Okay? So basically what you have to do is you have to add the two together, the two answers together to get the answer 5 halves. Graphically, what's happening here is when you're integrating from, hang on just a second. So basically you're integrating from 1 to 5 halves, so you're integrating under a function with a negative slope. And then when you get to 5 halves, you're integrating a function with a positive slope from 5 halves to 3. So you're basically getting these two pieces of areas together and adding them up. Okay, freeze the video here and read my comments on what you have to be careful with when you think about definite integrals. And it has to do with area. and I'm going to pick up on the next video and show you some properties of integrals.